Hi, I'm Loren, and I'm a chemistry student at Ghent University. I specialize in inorganic chemistry, but I'm also quite interested in organic chemistry and the research done in both branches for the development of new biomedical applications. This presentation will mainly focus on inorganic chemistry, more specifically on metal oxide nanoparticles, their synthesis, analysis, and usage. So, what is a nanoparticle? A nanoparticle is defined as a particle that is between 1 to 100 nanometers in size. The word nano is derived from the Greek nanos, which translates to dwarf. To get a grip of how small a nanoparticle is, you can imagine the following. Take an object which is 1 meter in size. Then make it 1 billion times smaller. That's the size of a 1 nanometer object. A metal oxide nanocrystal then is a nanocrystal consisting of metal and oxygen atoms. Their size and shape can be tuned by choosing the reaction conditions and reagents carefully. The images you're seeing right now are pictures of nanocrystals taken using an electron microscope. You can compare it to a normal microscope, but instead of using visible light to create an image, you use electrons. Now, how can we make these nanocrystals? One way to go about it is the so-called solvothermal synthesis. Here, a variety of solvents can be used to dissolve the reacting chemical compounds. A microwave can be used to heat up the mixture, but this is the normal microwave, of course. These specially designed microwaves allow us to work at elevated pressures, and they require less time to complete the synthesis in comparison to other high-pressure vessels. Another way to synthesize nanocrystals is the so-called heating up synthesis. Here, you start from room temperature and slowly heat up the mixture. Specific molecules are added during or after the synthesis to stabilize the formed nanocrystals. This allows the solid particles to behave as large molecules in solvents. We call this a stable colloid. A plethora of analysis techniques exist to characterize nanocrystals and their surfaces. For example, you've already seen the usage of electron microscopy to take pictures of formed nanocrystals. To determine if you actually created the crystalline material that you wanted to make, you can use a technique called X-ray diffraction. The peaks you see allow you to identify the crystal structure of the solid, for example, cubic. I mentioned before that it's possible to allow your solids to behave as large molecules in solvents. By making specific molecules bind on the nanocrystal surface, you cause the nanocrystals to repel each other. This way, they don't clump together anymore and you get a stable colloid. To determine if the particles aren't agglomerated, a technique called dynamic light scattering can be used. To put it briefly, a laser emits light into the colloid, and based on the scattering of this light by the suspended particles, you can gain information about the particle sizes in suspension. But the most versatile technique, in my opinion, to analyze nanocrystal surfaces is nuclear magnetic resonance. In this technique, a strong magnetic field is applied and allows us to extract information about molecules and their structure. More importantly, the different possible experiments allow us to distinguish molecules that are bound to the nanocrystal surface from those that are not. So, now you've created nanocrystals and functionalized them. But what purpose can they serve? Let's take a look at some metal oxide examples. Hafnium oxide nanoparticles have been shown to be catalytically active in the presence of a carboxylic acid and an alcohol. Here, both compounds first associated with the nanocrystal surface and then reacted with each other to form an ester. A control experiment showed that this reaction does not take place when the hafnium oxide nanoparticles are absent. Zirconium oxide nanoparticles have seen use in superconducting composites. A superconductor can be most easily described as a material that can transfer electricity without any resistance whatsoever when cooled to a certain temperature. Zirconium oxide nanoparticles are added to the superconducting material to improve its superconducting properties. As a final example, I'll shortly discuss what research I performed this year during my master thesis. We attempted to tackle some of the problems found in drug delivery, where sometimes a drug can have the perfect structure to perform its activity, but experiences difficulties to reach its destination. You could argue that alterations can be made to the drug structure to improve uptake in cells, but this in turn can cause its potency to decrease. We propose the following. Why don't we load the drug on a carrier while keeping its structure mostly intact? Imagine it as follows. The carrier is a bus and the drug molecule is a passenger. The passenger steps on the bus and the bus drives to its destination. After arriving on said destination, the passenger hops off and the bus leaves again. During my master thesis, we created the bus from this scenario. We created nanocrystals of zirconium oxide and synthesized a molecule which allows the crystals to form a stable colloid in water. We tested the stability of our nanocrystals in different concentrations of phosphate buffer and found that they remained stable in all but the highest concentrations, well above levels occurring in the body. Future research aims to improve stability further, attaching a drug to the ligand, and performing tests on live cells. Want to learn more? Visit following websites and feel free to contact us.